All right. So you've all done well on this, okay? I think that the hallmarks are here, like the dots are getting farther apart, and you plotted them from your data, so they were getting farther apart. The green arrows are getting longer, right? So this last green arrow, for example, is going to be the longest. Does that make sense? And I'm looking at your boards. Tell me what you notice about everybody's acceleration arrows. Yeah, on any board they're all the same length. Why is that true?
Because the acceleration is
Acceleration.
Right?
Yes.
She said, well, because the velocity is linear, so the slope is constant, so the acceleration is constant.
Yeah.
Cool? All right, so, well, that's what I heard you say. I mean, I don't know. Right? So when I go to put these on here, oh, I missed the velocity. And then this here is where the wheels are kind of falling off the cart. So what I'm noticing is that some groups have both acceleration and velocity. What do you have? Both acceleration and velocity. Bella, what do you guys have? Both?
Neither.
Neither. Okay, I like that. Ashley, what do you guys have?
Both.
Both?
We have both.
Both?
Yeah. Both.
Both?
Neither.
Oh my gosh. This is so exciting.
We got you.
So ready.
All right, now,
2 to 3.
listen. This is how this works. Okay? This is how this works. What we're going to do is we're going to have like a protracted discussion here where we're going to talk about it. You're going to say, this is why we did what we did. And then we're going to try to reason from evidence. Is that cool?
Yes.
All right. Sarah, you want to jump in?
Well, we put no arrows because if the arrows are representing what's happening at 0 seconds, and at 0 seconds the ball isn't moving.
Okay. All right. Go ahead.
Well, I had the same thought, but in theory, isn't the space between the two dots representing that time and in between the other time? That's why the arrow goes halfway, because it's representing also what happens in between that time. So from 0 seconds to 0.5 seconds, there is acceleration regardless of how small it is.
Okay. Go ahead, Dan.
Well, our idea was we're not counting the time when like the person's holding the ball. The minute they release the ball is when we start counting, and that's the instant starts accelerating. Also, if there was no acceleration, I mean, if there was no velocity at 0, you couldn't get to the next point.
Okay, Peter.
Well, to kind of add on to what he was saying, if there was no velocity or acceleration arrow, if the ball was not moving at 0, it would somehow have to get to the next point on the position and then start moving.
Okay, interesting.
I'm thinking that our start just like isn't on here because it's not moving at 0. It's moving between the first 2 points. So we're trying to represent that it's not moving at 0, but it's still going to like eventually move at 5.
So should there be 2 dots at 0? Yeah.
Well, 2 dots at 0, well, I mean, would indicate that it was there and that it was still there, like whatever time later. Yeah?
Alright, so what I'm thinking is that the dot right here is actually 0, and then the 2 lines are what's in between it. So like, this is when it's not moving, but this is what it is.
The points are more or less points on the graph. So when we took the tangent line, we're taking the tangent at that point. We're not taking the tangent line at that point plus half the tangent. Taking the tangent line at that point. So the acceleration, all these arrows are for that point. Nothing in between that point, so we only took the tangent line at that point.
That's a good point.
Yes?
I think there should be both arrows because it has to start at 0. So it starts moving from 0. It's not like completely stopped and then it just automatically moves to the next point. He has to start somewhere.
What was that, Sher?
He was just congratulating me.
Oh, he was congratulating me.
He just said good job.
Oh, okay.
That'll be a supportive group member.
No, I like it, thank you. Yes, Paul?
I know from like math class, like the derivative of like the bottom of like a parabola is 0. So
Mhm.
I don't know if that helps.
It does actually, right, but I think that's interesting, we actually have that represented here. So one of the things that has come up in this discussion is the question of what do the points represent? And what do the arrows represent? So in general, the way, and the reason that there is, confusion here is because when we're studying constant speed, the speed was constant. And so whether you were looking at an interval or an instant, it didn't matter. So do you guys know this word instant? I'm not talking about like instant pudding or instant rice, right? I'm talking about like the scientific term an instant. What that means is an instant is the smallest amount of time that you can conceptualize. Okay? That is opposed to a time interval, which would be between two instants. So a time interval in our case is like 0.5 seconds, so between 0 and 0.5, or between 0.5 and 1, or 1 and 1.5. Those are time intervals. What Chloe said, which was interesting, is she said, look, if we're going to use a tangent line at that point, then what we're really looking for is the velocity at that instant. You guys with me on that? All right, it's the velocity at that instant. So, did anybody push the ball down the ramp?
No.
What did you do with it? All right, and so if you look at the graphs up here, what's going on at 0 time? The instant of 0.
Position 0.
All right, so check with your neighbor, look at these graphs here, try to figure out what's happening here in terms of the instant of 0, okay? And see if that better informs your understanding.
Because it's not an origin.
I need to sign your yellow book.
I'm trying to find the yellow book.
12 or 9.
I feel like it's census
But
But it seems like, yeah, there's clearly no velocity.
On Tuesday,
It seems
right?
like there should be.
I'm gonna see. What time is it? Like, I don't know, 5, 7?
Probably 7 or 7. That's my guess, I don't know.
he said
Somewhere it's gonna be
mostly that you need to use that acceleration line.
All right.
Said you wanna share. I didn't know. Yeah, people do try to bring it. You always. Yeah, you're like the authors.
All right.
There's no velocity, but
I
there's
don't, what the
acceleration.
fuck do we do?
It just clicked.
It's there.
I just-
Right?
Yes.
Yeah.
All right, so,
Wow.
just a couple things about this. Just a couple things about this. One,
The graph.
let me just tell you how amazing you all
Thank you.
are, okay? No, both none or one or the other.
And you said that
We
part.
can't.
Yeah, I said both, or one or the other.
You
I didn't hear that
said-
part.
Both or none.
You lied.
You literally did say both.
Clearly, actually, clearly that did not get communicated because you all have either both or none.
It's only velocity.
Or one or the other.
No, I heard you.
Sorry.
I will say, just a general quick aside, how much I appreciate the discussion, okay? Now, not everybody has to participate in the discussion. I like when that happens. You're more than welcome to just sit back and listen. I just want you to be engaged in it, right? But you guys, this was a great discussion, and now we're gonna work on it. It's the difference between you thinking about it in the moment, let's talk about it, I'm gonna voice what I think, then we're gonna come to some sort of group consensus, If you contrast that with me up here just telling you what to do, that's very little learning happens on your part if I'm just telling you what to do, right? So you guys, you're killing it. I love it. It's fantastic. Okay, so the question is, if we look at our graphs, does that inform our decision making any better? In what way? Go ahead, Grace.
Because it's a visual representation of what's happening. So like on the positions versus time and the velocity versus time, they both start at 0 because they're parabolic. But the acceleration at 0 is still a unit, it's still a coefficient.
So she says, if you look, the value of the velocity at that instant of 0 is 0, but at that same instant doesn't have acceleration value. It does. Okay, hold on, Peter?
Yeah, I'm gonna say something similar to Grace. The velocity at the start is 0, because they start at 0, but the acceleration, I would more call it a constant. Like, the acceleration doesn't change. So even though it starts with no speed, it is still gaining it due to acceleration.
I think something that they said before I wanted to highlight it was, if it starts, I think it might even have been Peter, if it starts with 0 velocity and 0 acceleration, what would our problem be? It wouldn't be going anywhere, and that's why Jaden's like, do we need 2 dots then? No, I think if we just have 1 dot, even if it has 0 velocity, if we know that it's accelerating at that moment. And it's a weird thing to be not moving,
But have acceleration.
but still be speeding up.
Big brain.
Yeah.
But you have to be, because if you're not moving and you're not speeding up, then. Go ahead, Grace.
Is it because of like the idea of potential energy? When we move the ball and when we set it on the ramp, it's given that potential energy, and when we let go, it turns into kinetic?
That is a framework to understand this, yes. That is 100% a framework to understand
Job
this.
great.
We can talk about it in terms of energy, or we can talk about it in terms of force. There's something that's pulling it down the ramp.
Gravity.
And it's always pulling it down the ramp, right? Regardless of whether it's moving or not moving, it's still pulling it down the ramp.
Air resistance.
You know what? For this ball in the classroom, the air resistance is small, so we don't really talk about it too much. Yeah?
So on all of like these types of graphs, does the first dot not have like any sort of velocity whatsoever? Like even on ones without acceleration?
No, we have to, if it's not moving and not accelerating, then that would be different. But if you're an object on a ramp, definitely have to be accelerating. All right. So I want you guys to listen to what Jane just said. He's like, but if you push the ball, it would have it would have an initial velocity, right? So that's going to be an important thing, because how would this be different if you push the ball down the ramp? It wouldn't have 0 velocity at 0 time. It'd have something up here, right? And while you're pushing it, it might have some acceleration also. But we're going to talk about these things. We gotta baby step it.
So if you pushed it, would that be the y-intercept?
Yeah. So if you gave it some initial velocity, it would have an intercept. Like,
How would you measure that though?
Force.
put the speedometer.
Speedometer.
Are we good here? All right. So where you are, okay, you should have something called acceleration homework 1 in your hand. Okay. Now, instead of the ball, we're going to do this with the track. All right, so just turn around and look at me real fast. Okay. All right. So this is the far left end of the track, correct? This is 0 position. If I let this go, what happened to the car the whole time? Did it speed up the whole time? Yes. It did, right? So on homework 1, number 1, I would like you to draw the position, velocity, and acceleration for that car. And then draw a motion map just above the picture. All right? Do that right beyond it.
Is it like a sketch graph?
Yeah, I just want you to sketch what you think the graph's position, velocity, acceleration graphs are going to look like. Okay?
How many dots do you want?
I'm not sure.
How many dots do you want?
How 4 dots? 4 dots is good. 5 dots is good.
Mr. Bada,
Don't do like 10 dots.
so is constant velocity and acceleration the same thing?
No, your velocity. So this velocity is not constant, it's constantly increasing. Constant velocity would be something different. If your velocity is constant, then you're going to end up with that kind of graph there, that kind of graph there, and here. Because if your velocity is constant, you're not accelerating. Because the slope of that line is zero. Right?
That was
This is speed out, right?
Because the acceleration started at that had never started the game. Or I don't even know if we ever
Good.
played them.
Graphs.
Which they obviously was committed somewhere.
Yes, do the motion in again. Put it right.
Yeah.
Okay.
Or no, he can
Okay.
get his office.
Who said high cost?
It doesn't. The arrow is not important for our.
Are we doing the first?
This, and this, and a little motion. Probably.
That was the
So we're just re-sketching what we think it would be now.
I'm so sorry.
No, I should draw there. So we don't have a plan set up. We had a plan set up.
Yeah, I have,
Are you going to the game?
I'm going to the tailgate, but not the game.
It's linear.
Yes. Yeah.
Our friends performing at the tailgate.
Charlie, I want to see Charlie. Charlie, yeah,
Suffering. That's right.
they played that's cool.
wait,
What day or whatever? Yeah, they did one thing.
Oh, yeah.
It's gonna be cool.
Remember, the slope of this graph is this value. So this is linear, this one's horizontal.
Probably goes to like. Did anyone go to Kelly? What?
I don't think I've ever been to Philly.
I'm very nice.
Here, here's the problem. It starts away from the zero and gets closer to 1. All right, you guys ready? So when I look at this, all right, what we're doing, okay, is basically I have the same situation, but instead of the ball, we're gonna switch to the cart. Now, there's a couple things that are important. What does it say? Does it say that? What does that notation mean? Velocity when?
At zero.
At time 0 equals 0, which means you didn't push it. Is that cool? Here's a thing that is in the directions, but we don't often read it. It says, assume in each picture that the 0 line, the position 0, is the far left side of the ramp. Okay? So, what that means to me is that this here is x. Now, let me give you a graphic representation of this. Okay? Let me give you a graphic representation of this. I'm going to draw two shapes on my ramp. Okay? Up here at the top, I'm going to draw a star. Can you see my star? And then down here, I'm going to draw a hexagon.
Why didn't you just do a square?
Oh, I don't know. I just did what I did, man.
Or
Now,
a circle?
do those
But it's,
two shapes. Where do they manifest on my graph?
The left and right.
This way?
but like, it's,
I know.
I agree.
This way? This way?
Your axis and at your position.
So, here's the deal, and this is important. Remember, your graph is a representation of the physical object. This is a representation that's an abstraction. So, it's something like, this is two lines and a curve. We're trying to make meaning from that. So, where is the star?
Yours.
It's here. And where is the hexagon?
Next to the axis.
Wait, where did you get stars?
From both sides of the motion.
Because
Oh.
this position axis goes with your ramp length. Is that okay? All right. This is where the wheels fall off the cart. Are you ready? In your next example,
Right, yeah. But like, it's, pause. It's changing position for a second, and changing position is negative.
Oh, you're right.
It's about direction.
You're right.
the x equals 0 is still the far left side of the ramp.
It took me a minute to
Yes?
think about it.
So, this is number 2. See if you can't sketch it right meow. It's exactly the same, only different.
Yes.
You have it steep, getting less steep. This would indicate it was fast, getting slow.
Okay, all right, I trust you.
No, I'm not sure. Well, it starts,
Better?
no, it starts from the circle and it goes.
Like, so there's no,
Like this.
I mean, yeah, it has to start from the
So it doesn't start at 0.
there's
It
some,
ends at 0. Same.
Oh, I forgot.
You have your steep getting shallow, this way fast, this way down.
So balance your
So I mean,
story.
like, you start
No.
up here.
Oh, cool.
This car is moving to the left.
That is.
It's lots of zero is here, buddy.
I'm sorry, what?
All right.
Doing what now?
So, bell's gonna ring. Please do 2 things. 1, 3-hole punch that homework, put it in your binder. 2, erase your whiteboards, put them on the big stack. Please do both of those things before you go.